Hi, everybody. Welcome to this edition of Welding Wednesdays. We're going to be talking about electrical theory. I will let you know that I do have a bit of a dry throat, so might have to sip some iced coffee I got here on the side while we go through this. But yeah, this week, or whenever you're watching this, all about electrical theory. So we're going to look into arc welding. Why is it called arc welding? Why is electricity important for it? The basics of electricity in welding, and then some of our power sources.
Yeah.
So over here we can see a GIF, which is the correct way to pronounce it, in case you were unaware. But we see a GIF of welding process. Any guesses for anybody? Those of you who said submerged arc welding, 100% correct. Way to go. I remember there was a lot of times when I was teaching, especially with new students, who I would talk about submerged arc welding, and they thought it was the same as underwater welding, which I think is actually a mistake people make a lot. I think I did it when I was younger and was just getting into the welding world. But no, this is submerged arc welding. The arc is submerged under all that flux. All right, let's look at regular arc welding. So about 80 to 90% of all the welding processes are some form of electric arc welding. The big four that I've spoken about before, the ones that we kind of focus on here, are going to be SMAW or stick, GMAW or MIG, FCAW, flux core, or GTAW or TIG. There's also, even if you do not use arc welding process to join your metal, arcs are still going to be involved because 70% or over 70% of U.S. steel production is done by an electric arc furnace. And if you're unaware of electric arc furnace and how they work, it's actually pretty cool. It's similar to just how a stick weld works, where you're going to be melting material, you're going to mix it into something new. You have basically like flux in there, gathering up all the impurities. The impurities float to the surface with a slag, and then that pure or high quality or whatever steel will come out of the bottom. So what is an electric arc? It's a sustained electrical discharge between the electrode and the workpiece that will be in welding. We can see on the GIF here in the my upper right, an arc as they're disconnecting, looks like these electrical lines. I'm not an electrician, but pretty cool. When we create our arc, we first have to strike it, so establish that connection. If we do like a short circuit, basically, and then withdraw the electrode, which establishes that gap where that arc will live. And then there's temperatures of about 6,500 degrees Fahrenheit-ish generated with that arc. Plasma conduction, so once that arc is established and it interacts with a gas, including our atmosphere, then you start to ionize that gas. So ionization is just when we have turned the gas into a form that can easily be or conduct electricity. So there's some gases that have higher ionization, some with lower. Some will conduct electricity very, very well. Some will do a terrible job. But that is what the ionization is. And then the technical reason it happens is the energy supply to the gas surpasses the ionization energy of the atoms. So when that energy gets put in, atoms start releasing electrons, and those electrons are what allows for that movement of electricity through the gas. Kind of a picture representation of that ionization. So here we have a bunch of atoms. Looks like we have ones with one neutron, proton, one proton and two protons. So that's helium and hydrogen. You can see we got the little negative signs here. Those are all of the electrons that are orbiting. Add some energy into the system, and we start knocking off electrons off of those atoms. And then the electricity is flowing through these electrons, these like free electrons. All right, let's look at some basics of electricity and welding. We're going to look at some terms. So first term we're going to look at is voltage, also known as volts, indicated by the letter V. So voltage is the measurement of electrical pressure or potential energy. So basically it's all of the like energy you have to draw from. So the main role in welding that voltage corresponds to is the maximum gap that electrons can jump to form the arc. So that arc gap, that's what voltage allows us to establish and maintain. You have input voltage wherever you're at. Common input voltages in a regular like house or office is 120. Heavier industry or industrial power is 240. And then very heavy industrial power is 480. I like to think a lot of electricity like anything else that flows. It shares a lot of commonalities with like water, but also with gas. And so since we work for an industrial gas distributor, that there's lots of things that kind of go back and forth when it comes to electricity and compressed gas. So I would compare voltage to the PSI that's in a compressed gas cylinder that you can draw from. So when you have a cylinder, you roll it up into, let's say, your welding area. It's full of mixed gas. You're going to set it up to do some welding. Before you set it up, everything in that cylinder ready to go, that's going to be your voltage. There are phases to the power. You might have heard of single phase and three phase. So the difference between the two, just in case you didn't know, with single phase, you have one AC cycle. So an AC cycle, you can see down here, it's where we are going up positive and a negative. So one cycle is, we'll start at like neutral, we'll say, go positive, go negative, back to neutral. That's one cycle. We'll see a little bit with AC power, why that's important. So with single phase, that's one cycle. With three phase, we have three cycles. Single phase is less efficient, three phase much more efficient. Voltage stability, single phase, more fluctuation, three phase, smoother. Some typical uses: single phase, homes and small shops; three phase, factories, large welding shops; and then the welding machines that can run off of each of them. Single phase is light duty welders; three phases, industrial welders, cutters, that sort of thing. So I've had people like ask me before, why don't we do everything three phase? And the answer is the same as it is for almost every question you ask. Why? Why do you think? It's cheaper. So yeah, that's why we do single phase. It's cheaper. But three phase gives a more consistent power. When you're at home, stuff like that, you just don't need it in the same way. But if you're running heavy industrial machinery, it's very important not to have any interruptions into that flow of power. Another thing I learned when actually researching some phases is you can tell which power poles have what phase. So up here, this picture, three-phase line has those four different lines on it, and then a single-phase line right here has those two. So pretty cool. Good thing to point out to somebody when you're on a road trip or something. All right, so voltage is our potential, amperage is our flow. So it's the measurement of total number of electrons that are flowing. So it's a flow, also known as your current, and it is designated as I in a lot of different things. The I stands for, it's French, it's like incandescence or something like that. I'm not a good French speaker, but it's the same root of where like incandescent comes from. So role, it controls the size of the arc, and the way that I would compare it to compressed gas is it's like the PSI that's in the gas lines. So it's what's flowing through the lines from that source. Wattage is a measurement of power or total energy in your arc, designated by a P. Similarity to compressed gas, I would compare it to like the PSI or the CFH that's actually exiting the gas lines to perform the work. So if we think about a regular like GMA setup or GMAW setup, voltage is in the cylinder, amperage is what's in the lines, and then When you get to the machine and you're at the end of the like cable with your gun, the stuff coming out at the end of the gun, that would be your watts. So one way that we can figure out which component or how much of each component we have is a thing called Watt's law. So here you can see with voltage, amperage, we can get watts. And if we have two of those, we can get the other one. So this like first triangle down here, we see if we want power, that's going to be amps times volts. If we want amps, that's going to be power divided by volts. And if we have, or watts divided by volts. And then if we want volts, that's going to be watts divided by amps. So if we do a real quick, like a little math lesson here, if we look at the first one, we have our V, that's volts, at 5. We have our I, which is our amperage at 21. So what is our wattage? So we have to solve for P. So we can use this first one as far as an equation is concerned. So it's going to be P equals I times V. So we have 21 times 5. Ooh, really good at writing here. So 21 times 5 equals 105. So that means our watts are 105 for this first one. Second one, we have our voltage is 120. Our amperage is unknown, and our watts are 60. So we can go ahead and solve for our amperage. So it'd be this second one right down here. So to solve for that amperage, it's going to be our wattage divided by our voltage. So how many amps are going through this system? So 60 divided by 120. So 0.5. So half an amp will be going through that system. Makes sense to everybody, hopefully? All right. Next, we have ohms. So ohms is the measurement of resistance in an electrical system. Resistance is actually super important because that's what generates the heat for the weld. When that arc is passing through the atmosphere, it's rubbing up against atoms, causing friction, and that's the heat that melts everything. Resistance is found everywhere in your weld setup. So if we think about everywhere where there's an electrical connection, over a distance of cable, there's electrons lost. So everywhere where there's connection, electrons lost. Everywhere where there's any length of cable that the electrons are traveling through, some of them get lost. So whatever you set the machine to is not necessarily what's going to be at the end of your torch as far as your power level. This is really important when it comes to doing code welding and when you're qualifying procedures, because you have to go ahead and actually test what the power is coming out at the arc. Because the machine might say 120 amps, but because of connections, frayed wires, whatever it is, maybe you're getting 100 at the end of your electric holder. So that's why you would check that out. A similarity to compressed gas, I would say, is a regulator. So being able to take that like high pressure, regulate it down into a lower working pressure. I really like this photo up top where you have ohm constricting this passageway for the amp with the volt pushing. I think that does a great job describing how these things interact with each other. Another way to think about electrical movement that I've used is water. So we have high voltage, or we have the high potential, which is equivalent to, I said it already, but volts. Our current flow, what's that equivalent to? That's right, amps. We have a resistance, which is the same as ohms. And then we have our work, which is also known as wattage. So same sort of thing. How does the welding current work? So welding current works by electrons, so those things that orbit outside of the center of an atom. They're moving, and they move from a negative to a positive charge. I was once told that if you're an electrical engineer, it's positive to negative, but we're not. So for us, it flows from negative to positive. And then that current is that source of the heat. So as these electrons are running through the line, they're rubbing up against the atoms of the copper wire, and that's creating some friction, which is heat. And then when you go to weld, these electrons running through the atmosphere in between the end of your torch to your base metal, doing the same thing, rubbing, creating friction, generating some heat that we're going to use for melting. So here's a GIF of like a stick rod and kind of how it works as far as here is our rod up top. This is our arc. We're generating that arc. It is melting or the heat from it is melting our electrode, and it's also melting our base metal. And then the droplets are being kind of like carried or pushed. I don't know what the right way to say it is, but they're being like projected across the arc by that force of the electricity into that puddle where they'll go ahead and make the weld. So here's a slow-mo of the same thing. This is at 7,000 frames per second, but exact same thing we've seen before. So your arc will be here, melting our filler, melting our base. Then we have this filler being melted right there, and then being projected down into the weld pool. So we have three main polarities that we'll use when we talk about our flow of our current. The first one's going to be DCEN, which is direct current electrode negative. So how DCEN works is the electrode is negative and the work is positive. So we go ahead and electrons will leave our power source, come through our electrode into our work, and then the circuit is complete by it exiting the work and going back to the power source, also known as DCSP or straight polarity. This is good if you want to have like a greater deposition of your rod, because you're having more energy kind of in the electrode than into the workpiece. All right, DCEP, so electrode is positive and the work is negative. So the electrons will leave the work and travel to the electrode. So we can see the path here. We're again starting negative. Our electrons are traveling through our work up into the electrode. Then the electrode's completing the circuit, bringing it back to our power source. This is what most SMAW, I believe, is DCEP, or also known as reverse polarity. And then this is good for melting into your workpiece, usually, like getting deeper penetration. AC is alternating current, so this is where we're going to switch back and forth from positive to negative. And I talked before about a cycle, an AC cycle. So an AC cycle is where we go from like nothing to a negative charge, and then a positive charge, and then back to nothing. So this is one cycle. And that's also known as a hertz. So a hertz is an inverse of a second. It's 1/60th of a second. So with the AC frequency, or I should say the AC frequency is 60 hertz, and there's the electrons change directions 120 times a second. So basically 60 times a second, you're doing a cycle. Each cycle has two changes to it. So as far as direction, so that's why we have that total of 120 changes per second. That is something that you have the ability to adjust, especially when you're doing welding on aluminum. You can adjust that frequency. So that would be how many times it cycles per second. As I mentioned, for aluminum, we do that because we have a special property that kind of happens with aluminum and aluminum welding. So aluminum is different than like steel. When it comes to corrosion, steel will corrode or rust until there's nothing left. When it comes to aluminum, you have a thin layer of aluminum oxide that forms, incredibly thin. And underneath there is that pure, softer aluminum. So what happens is if you're trying to weld it, that oxide layer melts at 3,600 degrees, and the base metal underneath melts at about 1,200. So it's very, very thin. So you have to put in enough juice to be able to melt that. But then once you melt that outer oxide layer, then you have 3 times as much temperature as you need to melt the base. And so you just melt the whole thing and it's a mess. So with AC, what happens is when you're doing the negative part of the cycle, you're welding. And when you're doing the positive part of the cycle, you're breaking up oxides from the surface. So that's how the AC works with aluminum. When you're positive, breaking up the surface, negative welding. So then each cycle, let's say we're starting going positive. So we're starting a cycle. It is clean. So we'll do this here, plus or minus. So clean, weld. And then you can just repeat that as many times as you need to make the weld. And you can adjust how many of those happen per minute. When you usually increase frequency, that'll make like a narrower bead, lower frequency, wider bead usually, that sort of thing. For constant current or voltage, you can hear people describe machines as a CC or a CB. So with constant current, what happens is you start with a high voltage and then a low amperage. And then as you establish the arc, the voltage helps you establish the arc. Once it's established, you don't need that voltage to be that high. So your voltage starts to drop right here. And then your amperage increases to the amount of amperage you need to actually weld. So the reason it's called constant current is because if you take like any point on this curve and you go ahead and you multiply your voltage by your amperage, you should get the same wattage anywhere on this line. So the power is the same. It's just it goes from high voltage to low amperage to high amperage. When it comes to constant voltage, there's little voltage fluctuation. So right here we can see this line. That's your constant voltage. You can adjust your amperage though while you're doing like GMAW and FCAW by changing your arc length. So if you increase your arc length, there's more resistance. Arc length decreases, less resistance. So that can change how much energy is being put into the actual weld. Open circuit voltage. So this is what's available before you strike that arc with like SMAW. A great way to think about it is like a hose, right? So top picture, you have a garden hose, it's turned on. You have all that water pressure ready to go. Once you turn it on, then the water goes out a pretty good distance because it has all that force that's been like bottled up behind it. But once that force has been relieved, then you get a steady flow. And so the flow is less than that initial like burst of water. So that is exactly what happens when you strike a stick electrode. You're starting with all that potential. This larger like burst or flow of water or electricity, that's how you establish your arc. And then once the arc is established, you don't need that burst anymore. So then we go down to like a really steady flow. So common voltage for welding is usually between 17 and 40 volts. Grounded connection. So I wanted to put this in because there's a couple things with the welding industry that bug me. This is one of them for whatever reason. But it's calling your work cable and work clamp a ground. So those are not grounds. What your work cable and your work clamp do is they help complete that circuit so you can establish and maintain that electrical arc. What a grounded connection does is it provides a safe path for excess current to flow into the earth. So it prevents shocks, damage to equipment, fires, that sort of thing. So I think I'm covering up part of this here. But basically, like if you have some equipment and all of a sudden there's excess energy in it from whatever reason, if you do not have a ground and you touch it, that excess energy can go through you, basically, because you become the path of least resistance. I always tell people we are big bags of salty water with a ghost trapped inside. So, our primary purpose on Earth probably is to keep that ghost in there as long as possible. And if you go ahead and touch something highly energized and it doesn't have ground, that ghost is going to come out. So that's where the ground that hooks up to your power source. So instead of the excess electricity being in the equipment and you being able to be the ground for it, instead that excess will go immediately into the ground to be dispersed, so it's not actually going to hurt anybody. All right, so finishing up for this session, we're going to talk a little bit about power sources. So power sources, what they do is they convert input power to a suitable form for welding. And it's kind of crazy if you haven't noticed this before, if you haven't done a ton of weldings, but depending on the machine, depending on how the electricity is being manipulated, it feels different. You can tell differences. There's differences in types of machine and brands, all sorts of stuff as far as how that electricity is flowing. You can tell if you got good clean input power because you have very smooth flowing electricity. The welding is very smooth, very controlled. If you have more dirtier input power where it's not as consistent, or maybe there's something with the machine, then that arc will not be consistent. It'll be jumping around a lot more, harder to control, that sort of thing. So 4 big types of power sources that we work with. The first one would be a transformer. So that's a constant current, as we talked about before, like stick. So transformer converts high voltage, low current AC, so stuff that's coming from your input source, from your plug in the wall, to a low voltage, high current AC for welding. Outside of buildings and stuff like that, you usually will find big transformers too that are taking everything from the line voltage and turning it into, or converting it into the useful voltage for whatever it is, the house or the factory or whatever. Then you have a rectifier. A rectifier is in constant current and constant voltage machines. So what the rectifier does is it converts that AC power to DC using things called diodes. So it provides the DC, so that direct current, polarity, plus or minus, which gives you better arc stability. An inverter uses high-frequency circuits to convert the input from AC to DC, so like a rectifier. Then it goes back to high-frequency AC, and then finally it rectifies it back into a very stable DC. So what this allows you to do is really shrink the machine, because you're, instead of using mechanics to do this in a transformer, you're using high-frequency circuits to change that electricity into the different usable forms. So you get a lot more efficient electrical use, and then in a lot smaller package. Downside is it's more expensive to fix a lot of times, because when you lose a circuit board, those are pretty expensive. And then finally you have a generator. So a generator has an engine in it that produces electrical power for welding. It can supply AC, DC. Generators are great for somewhere, like field welding, because not only can you run welding off of it, some of the generators are also air compressors, or you have the ability to hook up an air compressor or hook up other types of equipment you need, because it'll have excess power usually. So like a grinder, whatever, you can plug it into that. I wanted to do a real quick comparison of these. On the bottom, I tried to do it to scale, kinda, but so I think you get the gist of it. But if we look at our 4 sources: transformer, rectifier, inverter, generator. So this first one here is a transformer. You might have seen it out in the world. I saw those at Home Depot. That's old Lincoln Buzzbox, or Tombstone, as they call it. Next one is an ideal arc. So this is your rectifier example. And then we have the inverter. And then finally this Ranger is our engine drive. So you can see the number up top, in blue, that's going to be how much it weighs, and then the price. So we have transformer, about 100 pounds, $700. Very simple, can only stick weld. But I tell you what, great thing to have in the garage, or if you're on a farm, you're doing some light repair work or some very light fabrication work that does not have to be super precise on things. Works great. for the rectifier, this is something that's going to be used in a much larger like industrial setting. So you can see difference in weight and price. Now, this is the really interesting one to me, is the inverter. So the inverter is 300 pounds less than this transformer rectifier system, and it is about the same price. So that's that difference there, where you get something so much lighter, way more efficient, but the price is the same or even sometimes more because of that complex circuitry inside. And then finally, we have our generator. So generator here, about 600 pounds. And then the most expensive of them all, but that makes sense. It's a big engine. So, and then off the front here, I talked about you can plug in stuff. A lot of times there'll be like outlets and whatnot. So you can plug in extra things there to charge or to run. All right, that's it for this time together. As always, here's some of the resources I used. If you have any questions or need anything, please reach out. If you have ideas for things you'd like me to cover, I'm open to that too. All right. Appreciate you guys paying attention, all you folks. Here's our information, and I'll see you next time. Bye.